Alrighty, let's have a look at modeling some asymptopic behavior. And in particular, we're going to be thinking about temperature, because temperature is a great example. If you take a really hot coffee and you know, on a coolish day, then the temperature, capital T over little t time, is going to slowly decay towards the room temperature. And notice at the beginning it's going to quite quickly approach, and then after a little bit of time it's going to take slower and slower to actually reach that temperature. Alternatively, if you take, say, the carton of milk out of the fridge, well, it's going to be approaching from the bottom instead. So we're going to be having a look at these different exponential functions that model t and t, where little t is going to be time and big T is going to be temperature. And we're going to be using degrees Celsius. Alrighty, so the temperature on a hot summer's day in Cloncurry is 47 degrees. Sally buys a milk drink which is removed from the refrigerator at 4 degrees. After 10 minutes, the temperature of the milk is 16 degrees. The warming can be modeled by an exponential equation, T, capital T, equals A times Z to the minus T plus B, where n be integers. T is the time in minutes after taking the milk out of the fridge. Z is the rate of warming per minute. And T is the temperature, capital T, is the temperature in degrees Celsius of the milk. Determine the value of the constant term, given that the locker stays at air temperature. So this comes down to what we were talking about. What we basically think when we're thinking of temperature is that the air temperature, well, that's just going to be our equilibrium state, or our basically where it's not going to go past. And that for us is our asymptote. Right? Because our asymptote is this point that we basically never reach, but we get very, very, very close to. And room temperature can be thought of in the same way. You get really, really close to the room temperature. Basically, you're on it, but theoretically, maybe you're a couple of degrees above or below, depending on which way we're going. So we're going to say that the room temperature is going to act like the asymptote. And since the room temperature is 47 degrees, and our asymptote is controlled by this, well, we know that B, our constant term, is going to be 47. No working out needed. Well, from there now it wants us to calculate A. Okay? Well, we actually have a point. Part A done. Part B. We've actually been given a point. In fact, we've been given 2 points. The first point we were given is that after 0 minutes, it was 4 degrees. And then the second point we were given was that after 10 minutes, remember T is time in minutes, it was 16 degrees, which makes sense because it's warming up. So we've got 2 points and we can substitute those into our equation. So since our equation is T equals A times Z to the minus T plus B, but we know B now, it's 47, we worked that out in A. Now we can sub in our first point, 0, 4. So 4 is over here, equals A times Z to the negative 0 plus 47. Now Z to the 0 is 1, A times 1 is just A, plus 47. Oh well, I need to subtract 47 from both sides. 47 of 4 is going to be negative 43 is A, and there's my A value. So my new equation, leading into part C, where we're going to be calculating the last variable, Z, our last constant in the equation, is going to be T equals negative 43 times Z to the minus T plus 47. And this is where we're going to use our second point that we found. So we're going to sub in 10, 16 to look for Z. So 16 goes on the left-hand side, equals to negative 43 times Z to the negative 10 plus 47. Take 47 from both sides. In this case, it's going to be negative 31 equals negative 43 times z to the negative 10. We can divide both sides by negative 43. The negatives cancel, so we just get 31 over 43. 31 is a prime number, so it's not going to simplify in any way. And now we need to just take the negative 10th root of both sides. So we're going to have to use our nth root button. We're going to be putting negative 10 there. Chuck that in our calculator. 1.033. To two decimal places, so 1.03. Alrighty, so there's A, B, and C done, and we've now got our equation for t. We've worked out all the constants. So we've got t is equal to negative 43 times 1.03 to the negative t plus 47. And notice here that our equation meets all of the requirements. Little t and capital T are x and y values, and the other three are constants. Note that the a and b values, the number at the start, negative 43 and 47, are both integers, which is what it was given in the question. So we've now got our kind of equation, and now for part E, let's see what it wants us to do. Once the temperature of the milk reaches 25 degrees Celsius, it is not safe to drink. How long can Sally leave it in her locker? Well, when is the temperature equal to 25 degrees? So 25 is equal to negative 43 times 1.03 to the negative t plus 47. Now you could absolutely just use graph mode to solve this, but we now have the tools to algebraically solve it as well. So let's take 47 from both sides. So now we're going to divide both sides by negative 43. And the only thing we've got to do left is take the log base 1.03 of both sides. 22 on 43 equals 1.03 to the negative t. Take the log of both sides. And on the right hand side, we're just left with negative t, which isn't quite what we're looking for, but it's pretty close. And on the left hand side, we're just going to get some constant, which is negative 22.67. Since it's equal to negative t, well, we can just make that positive t and make that 22.67. And this is in minutes. Now, you could leave it for 22.67 minutes, but that probably doesn't make as much sense as rounding it to something a bit more sensible. So let's say, no more than 22 minutes. As our final answer. Alrighty. So, finally, we've done a little bit on temperature and exponential functions. Alrighty. I'll see you in the next one. Goodbye.